Hello there, and welcome to Lecture 7 on the method of partial fractions. So in this lecture and in the next lecture, we're going to be talking about integrating functions of this particular type. So we're going to be developing a strategy to handle integrals of the form f of x divided by g of x, where f of x and g of x are polynomials. And I'm going to specify that g of x should not be the zero polynomial because we cannot divide by 0. And when you have the ratio of two polynomials like this, we refer to this as a rational function. So we're going to be learning how to integrate rational functions in this lesson and in the next lesson. I'm actually going to call this part 1 because there is going to be a part 2. All right, let's take a look at this example here. So we're going to use the fact that this rational function, 3x plus 11 over x squared minus x minus 6, we're going to use the fact that this equals 4 over x minus 3, 1 over x plus 2, to evaluate the integral of that rational function. Okay, so the problem would like us to integrate this function right here, but we're given in the directions that this fraction can be split up into these two smaller fractions. And this is what partial fraction decomposition means, is you take a complicated looking fraction and you split it up into more bite-sized pieces. So that's what we're going to be doing. But I'm going to use the fact that I know this in advance. And I'm going to say now that this is equal to 4 over x minus 3 minus 1 over x plus 2 dx. So I'm going to substitute that. And then before I do this, let me remind you of some important rules from Calculus 1 that you should remember. So if you have the integral of x to the n dx, and we're going to say in this case that n is not equal to -1, but it can be any other constant, then this is equal to x to the n plus 1. So we add 1 to the power, and then we divide by the new power. So that's how you handle that integral if n is not equal to -1. And I just wrote that really closely, so I'm going to move that over. However, if n is equal to -1, then that means that we have 1 over x. And this is its own special integration rule. The integral of 1 over x is ln of x, ln of absolute value of x plus c. And I should also put a plus c, I think, after this as well. So these two are important. They're going to be important when we're doing this lesson as well as future lessons. So make sure you know these two. So let me return to this. I have a constant over x to the first power for both of these. It's OK that there's constants down here as well. The way we integrate 1 over something with x to the first power is we use ln. So the integral of this first term is 4, constant 4, ln of, and whatever the denominator is, x minus 3. And if you took the derivative of that, you would get back to where you started here. And then this is going to be ln, so minus ln of x plus 2 plus c. So both of these were 1 over x to the first power, so they both are ln based on this rule right here. The question is, though, how did they know that this complex-looking fraction here, this rational function, splits into these two easier things? Well, we're going to spend this lesson and the next lesson, the bulk of it, learning how to do just this, splitting up a fraction into two smaller fractions, and then we can integrate the easier pieces. So this is the start of that here. This is going to be the first half of the cases we're going to cover. So I'm going to organize it in a table for you as usual. And this is the method for how we split up these fractions. So the first thing we need to look at is what factors are in the denominator. So down here in this denominator, if you factor this, this was x minus 3 and x plus 2. So we had two linear factors. So if you have a linear factor, we'll say it's ax plus b, then what you need to include in your decomposition of the fraction is some constant capital A over the linear factor ax plus b. That's going to be present somewhere in the decomposition. And the other case I'm going to talk about right now in this video is if you have a linear factor, but it's repeated. And what I mean by that is I don't have just this in the denominator. I have some kind of k as well, where k is going to be greater than 1, and k is an integer. So I have a multiplicity for this root, for example. Then for however many there are here in the denominator, I'm going to need just as many corresponding over here. So I need some constant a1, ax plus b. That's supposed to be a plus right here. Let me erase that. So ax plus b plus a2, ax plus b, and then we would square it. And you continue this all the way up to some constant a sub k, a of x plus b to the k power. So for however many of these repeated ones you have to have k of these to match the number of these. OK, so let's look at this example I have on the board now. So our goal is to split this up into more bite-sized pieces and then just integrate the pieces separately. So what I'm going to do first is I'm going to work on writing this as the sum of 3 easier to deal with fractions. So this is case 1, because they're linear factors on the bottom, and none of them have a power here. None of them are repeated. So this is just case 1. So for each of these linear factors that are not repeated, I need a constant over the factor. So I'll have b correspond with x plus 1, and I need a c that corresponds with x plus 2. And if this wasn't factored for you in the denominator, you'd have a step before this where you need to factor the denominator yourself. But this one's nice, and it's already factored for us. OK, so we have to figure out these 3 unknown constants. Well, what we can do is we can multiply both sides by the least common denominator. So LCD stands for least common denominator, and it's all of this. So imagine multiplying this on both sides of the equation. So on the left side, it would be x plus 1, x plus 2, times this fraction. And in this one, everything would get multiplied by x plus 1, x plus 2. And you can think about that distributing to all of these things here. So if we multiply the left side by the common denominator, it cancels with itself, and you just get x squared plus 1. Look what happens on the right side. The x will cancel here, but the a is still going to be with the x plus 1, x plus 2 after distributing. Similarly, the x plus 1 will cancel here, but the b will still be with x plus 2. And then c is going to still have the x and the x plus 1. So that's where we are so far, just multiplying both sides by the least common denominator. There's typically 3 methods that people go over to solve for these constants. And I'm going to gradually just introduce them to you as they become kind of applicable. So this is my first one that I'm going to show you. This one I'm going to call this method 1, which will be substitution. So my idea is this is supposed to be true for every single x value, every real x value. So if you are clever and pick an x value that's nice, you can get at these a, b, and c values. So let me give you an example. Let's pretend x is 0. This is supposed to be true for every x. So if you plug in 0 on the left side, you get 1 equals. If you plug in 0 here for x, you get 2a. However, this and this are both 0 because you have a factor of x sitting here. So this lets you know right away that a is 1/2. And that's because I picked a clever choice for x. And I can do that for the two other values too. I could pick -1 and I could pick -2. So if you plug in -1, you get 2 equals. -1 cancels this first term, but here I get -1 times 1, so I get -b. And this one cancels here. So if I just move that negative over, I get b equals 2. I'm sorry, -2. B equals -2, right? Because we moved the negative over. And then for this one, if I plug in -2, I get 5 over on the left side. This and this go to 0, so then this, I have -2 times -1 is 2. So I have 2c, and then this means that c should be 5 over 2. So often, over 50% of the work is just figuring out what the constants are. So now that I have this, you can go back up to the original. So this means that the original integral, x squared plus 1 over x plus 1, x plus 2, you can replace that with something nicer to work with. It's actually equal to a, which was 1/2, and then 1 over x, plus, but I'm plugging in a -2 for b. So I have -2, 1 over x plus 1. And then my last one is plus c, which is 5 over 2. And then it's 1 over x plus 2. And notice I'm just bringing those constants out front right away, just to kind of make it easier. And then this I can just do each individually using the rule I talked about over there. So this is 1/2 integral of 1 over x is ln of x, minus, this is 2 ln of x plus 1. And then this one right here is 5 over 2 ln of x plus 2, plus c. This is the correct answer. I imagine that maybe like an exam question might take these and use the log rules just to be cheeky. So you can bring any constant in front can come up as power. So you get x to the 1/2 here. Here you get ln of x plus 1 squared. You bring the 2 up, and then this would be ln of x plus 2 to the 5/2 plus c. And you can also do those log rules where if you're subtracting 2 logs, you can divide the 2 values and multiply. So here I would do this divided by this plus this. So it would be log of x to the 1/2 over x plus 1 squared, and then times x plus 2 to the 5/2. Just like that, plus c. So this would be my complete answer. So the idea here is you're taking something that is a complicated rational function, and you're splitting it up into bite-sized pieces. And the way you get there is you do algebra. This is just method 1, but in a few more examples, I'm going to show you the 2 other methods in action. So I'll see you in just a second for that. OK, welcome back. So you may have noticed that the table has grown a little larger. So I've introduced 2 new cases into the table. You could copy them down for now, but I'm going to get to them later. And in the next video, we're going to talk about these a lot more as well. But I just wanted to be complete and write all the cases here now. So we'll get to that soon. Here I want to talk about a definition before I go any further. So a rational function, f of x over g of x, is called proper if the degree of f of x is strictly less than the degree of g of x. And remember, the degree of f of x and g of x are polynomials. So degree is the highest power present amongst all the terms. So we say this fraction, or the rational function, is proper if we have a lower power on the top. So let's take a look at this example. Here f of x is this 4th degree polynomial, because 4 is the highest power. And then g of x is this 3rd degree polynomial. So before we even get started with our process we just learned in the last problem, you must have a proper fraction before you can get started. So we must have a proper rational function. We have to in order to do our method. So if you don't see that you have a proper fraction, even if the powers were the same, this would not be proper. You have to have it be less on top. So we have to use long division. This is kind of becoming a theme. We had to do completing the square last time, which is like an Algebra 2 review thing. Long division is something that you learned in Algebra 2 as well that's not very liked. But I'm going to review it with you right now. So what you need to do is you need to divide the denominator into the numerator in order to fix this. So I think what I'm actually going to do, because I think it's helpful, is this polynomial has no x to the third power. So I'm going to put 0x to the third power as like a placeholder. I think that's like infinitely better to look at. So I'm going to do that instead. OK, so what you do first is you figure out what needs to go here so that this times the first term is equal to the thing inside the division symbol here. So we have x would go here. So x times x to the third will make this first term match, which is what you need. And then you take this x and you multiply it through by the rest of them. So x times this, you make sure you consider the signs as well. You get negative x to the third. This would be negative x squared plus x. And just like long division from like the third grade, you draw a line here and you subtract. And it's a subtraction to all of them, so you have to be really careful at this stage of double negatives. So this first part will always go to 0 if you've chosen correctly. 0 minus a minus would give us a plus x to the third. Negative 2 minus negative 1 is negative 1, because you get another double negative. 4 minus 1 is 3x. And then you bring down the next one. And then you ask yourself, can you go again? Is there another number you can multiply by? And you can. It's a plus 1. Because if you do 1 times the first one, you do the whole process over again. You get x to the third. And this is minus x squared minus x, and then plus 1. We're going to do subtraction to all of them again. So you get 0. This is also 0, which is very nice. They match. This is not. You get 3 minus and minus 1 is 4x. But then these also cancel. So now the power of this is 1. And it's strictly lower than what you were dividing by. So you're done. This is called a remainder, because you can't divide this into this anymore. So this is my remainder. And let me show you what that turns our integral into now. So this now becomes, here's all the whole pieces we were able to divide out. This is x plus 1. My remainder is going to be 4 over x divided by what I divided by. So my divisor here, which is x cubed minus x squared minus x plus 1. So what I'm saying is that this is equivalent to this. And now you should notice that this is a what? It's a proper fraction. Proper fraction. Or rational function. I don't know, whatever the definition is. It's proper. These two pieces are very easy to integrate. So the integral of x is 1 over x squared. And the integral of 1 is x. So now I'm focusing on that constant 4. I'm going to bring that out. Focusing on this integral right here, because this is the part that I'm stuck with now, is this right here. So what we need to do is we need to take this fraction right here, and we need to use partial fraction decomposition to break it up into smaller pieces. So now we're going to focus on just this fraction right here. This is x divided by, and here I'm going to use factor by grouping to factor this polynomial down here. So you can factor out x squared from both of these two terms, and that leaves you with x minus 1. You can also factor out a negative 1 from the last two terms, and you'll get minus 1, x minus 1. So actually, factor by grouping tells us that this is x squared minus 1 times x minus 1. But then this is a difference of squares, so this fraction actually factors into x minus 1 squared, x plus 1. And now here I'd like to break this up. So notice we have case 2 and case 1 because I have a linear factor and it's repeated. There's a 2 here. And I have a linear factor that's not repeated. So the complete form of the partial fraction decomposition is going to be a. And this is going to be for x plus 1. And then for this repeated one, I need 2 of them. I need a b, x minus 1. And I need a c, and I need an x minus 1 squared. So for as many of these that there are, I need just as many of these terms. OK, and the goal is to figure out what a, b, and c are. So now I'm going to introduce to you a second method of finding these constants. So this is called, I'll call it method 2. This is called the cover-up method. And this applies to all terms with the highest power factors in its denominator. It applies to those constants that have that. So the highest power of x plus 1 I see is this one. So we can use cover up here. The highest power of x minus 1 I see is this one, this squared. So we can use cover up here and here. So we're going to be able to find a and c using the second method called the cover up method. So what you do is you consider which x value for this one makes it undefined. So this would be x would be negative 1. And this allows you to find a. So what you do is you cover up the x plus 1 factor in the denominator here. I can't do that because I'm on the other side of the board, but well, hold on. Let me run over there. I'm going to come over here. And now I'm looking at this backwards. But right here, this is the x plus 1 factor. So cover that up and plug in the x minus 1 into each of those. And that instantly tells you what a is. So plug in the negative 1 here and here, and you're going to get negative 1 over negative 1 minus 1 is negative 2 squared is 4. And just like that, you have a. I'm going to do the same thing for the other highest power factor here. So this is x minus 1. So x equals 1 would make this term undefined. Plug in the 1 here after covering up the x minus 1, and you get 1 over 2. So now we've found out what a and c are. We're going to use a third method, the final method I'm going to show you, to find out what b is. So we're going to start this the same way as the last problem. Multiply by the LCD, which this time is x minus 1 squared, x plus 1. Multiply that to every single term. And we're going to have all the same cancellations like we did before. So if you multiply both sides by the LCD, we're going to get x equals. The x plus 1's cancel. I get a x minus 1 squared plus b. One of the x minus 1's cancels, so I still have one of those. And then for c, the x minus 1's cancel, and I just get x plus 1. All right, and another thing that I know now is that a is actually equal to negative 1/4. So allow me to do this, please. I'm just trying to save some space. So a is negative 1/4. And c, oops, sorry, this is supposed to say c, right? C corresponds to this one, so that was c, but it doesn't matter. We're erasing it. We're putting a half right there. And then method 3, the final method, is called equating coefficients. And here's the idea. On the left side of the equation, I have 1x. Okay? I also have 0x squareds, right? On the left side, I have 0x squareds. What are my x squareds over here? So 0 equals, well, if I FOIL this out, for this term, I would have negative 1/4 x squareds here. Would I have any x squareds here? Yes. I would have b of them, right? I'd have x squared. There's a b in front of that. This is bx squared. This is 0x squared. Here, for the last one, I don't have any x squareds, right? It's just 1/2 x, 1. So this has to be true. So these two, b and negative 1/4, have to add up to 0, because I'm supposed to get 0 on the left side. There's supposed to be 0x squareds. So this tells me that b minus 1/4 is 0. So b has to be 1/4. So what we're doing is we're comparing both sides. Left side had 0x squareds, and then the right side had x squareds. You just have to figure out how to make them 0, just like the left side. So this tells me that b is 1/4. So now I'm going to take this, what I have right here, and I'm going to use my constants to write out the final form of the integral. So down here, it's going to be 1/2 x squared plus x plus 4 times the integral of, and I'm going to split up this fraction. So I have a, which is negative 1/4, 1 over x plus 1, plus b is 1/4 right here, and then x 1 over x minus 1, and then c was 1/2, so I get plus 1/2, 1 over x minus 1 squared. So I need to integrate this. OK, well, this is 1/2 x squared plus x plus 4 times. If you integrate this, you get negative 1/4 ln of x plus 1. The next one is going to be 1/4 ln of x minus 1. And this one is going to be 1/2. And then this is not x to the first power, right? This is x to the negative 2. So how do you go backwards when you have x to the negative 2? Well, you would just get this factor, x minus 1 to the negative 1. And then what I would need to do is I'd need to change this to a negative sign to integrate that. So now if I go forward, I bring the negative 1 down. It's plus, and it goes to negative 2 like I need. This is plus c. And then the last thing you could do is you could take this 4 and I guess distribute it into all of these. So the final answer is going to be 1/2 x squared plus x minus ln of x plus 4 plus ln of x minus 1. And then minus, the 4 is distributing. I get 2 x minus 1 to the negative 1 plus c. And that's my final answer. And it looks OK to me, which is good. All right, so the final thing I had in mind after all of this kind of took over the board is I didn't want to do necessarily another problem. I just wanted to practice writing out the form of a partial fraction. So we're going to write the general form using these 4 rules. It all comes down to the factor denominator. So they've factored the denominator for us. Notice I have linear factors here, and I have irreducible quadratic factors here and here. And this one's repeated, so I'm going to need many of these. So if I was going left to right, this is what it would look like. A linear factor needs an a over x. Here's another non-repeated linear factor, case 1. This needs a b over x minus 1. This is an irreducible. You can't factor this. It's quadratic. So you're in case 3. You would need a cx plus d over x squared plus x plus 1. And then this one, there's 3. It's repeated, and it's quadratic, and it's irreducible. So for this, can't factor that. I need 3 more. So this would look like an ex plus f over x squared plus 1. I need another one, so gx plus h over x squared plus 1 squared. Remember, we increment these as we go along. And the last one would be I have to do my alphabet, ix ij over x squared plus 1 cubed. So this would be the form of the partial fraction decomposition, just considering all of these. So you should have these 4 things memorized, the way you would break this up. Luckily, we don't have to do a problem like that right now, because that would require a lot of work. OK, so this was part 1 of our method of partial fractions. In the next part of the video, we're going to be focusing even more on cases 3 and 4, because I really didn't incorporate these yet into these types of problems. So I will see you then. Have a nice day.